All right, so 2.6 continued from yesterday. We're talking about related rates. Again. So everything we do today is going to be over time. So we're going to figure out how quickly are things changing over time. So continue from yesterday. We're still talking about 2.6, but we're going to talk about we're going to talk about some practical applications of related rates. See, okay, it's not good. Like I said, my handwriting's not good, just a little bit better than it was before. Okay, so practical applications. What I want you to do is look, please, on page 150 in your book. I think I already told you that. Page 150. And it is telling you, in example 2, it's called ripples in a pond. It is talking about a pebble being dropped into a calm pond. So here we have a very, very nice glass, like a pond that has at the top is like glass. It's not moving, it's perfectly still. You drop something in it, what happens? Yeah, it ripples come out and it makes what shape? A circle. It makes a circular shape. So it goes on in here to talk about how the radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? That sounds horrible. Like I read that and was like, oh, yuck. But we're talking about a circle, right?
Yeah.
No. We're talking about the area of a circle. What is the formula for finding the area of a circle?
Pi.
It is up there. If you have, okay, now that would be a formula that I thought maybe you would have remembered because it comes up often enough. But when you're doing this, the first thing that you need to do is figure out what formula you're going to use. And in this case, we're talking about a circle getting bigger and bigger and bigger. So the formula that we're going to use is A equals pi r squared. Let's find the derivative of this all over time. What is the derivative of A?
dA over dt.
What's the derivative of x?
1.
1. Yes, 1 dx dt, right?
Yeah.
So what's the derivative of A?
dA dt.
1 dA dt. So we have dA dt is equal to, now remember pi, sometimes we forget that pi is a number. Imagine for a moment that it was a 3 instead of a pi. What would be the derivative of 3r squared?
2pi.
It would be 6r, right? You just multiply the 2 and the 3. Well, it's not a 3 though, it's a pi. So when we find the derivative, we're going to get 2 pi. You okay with 2 pi?
Yep.
2 pi r. But we found the derivative of r squared, so it's going to be dr dt. The hardest part is done.
Wait.
I have a question. Why is it t?
Because we're applying this to time. We're figuring out how quickly is the area changing in comparison to time. How quickly is the radius changing in comparison to time, all right? So I'm going to go back to my problem now, and it tells me in there that when the radius is 4 feet, that means, using your derivative here, we now know that this r value is 4 feet. So r is 4, good information. It also tells you in here that the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. The radius is increasing at a rate of 1 foot per second. What is this? Which one of those variables, which one of these unknown things did they just tell us? dr dt. The radius is changing at a rate of. So that means this right here, dr dt, is equal to 1. Your job is to figure out, the question here is, go back to my book here. It says, at what rate is the total area of the disturbed water changing? Our job is to figure out dA dt. How quickly is the area changing? We have to solve for dA dt. So dA dt is going to be equal to 2 times pi times the radius. What is the radius?
4.
It is 4. 2 times pi times 4 times dr dt, which is 1. So we have 2 times pi times 4 times 1. I believe that is 8 pi.
Hold on.
So we don't have to do decimal.
You don't have to do what?
Decimal like
You don't
No,
actually
leave it in
have to
terms of pi. Yep. Samari, what did you ask me? Larissa.
When you took the derivative, I see you put the 2 in front. How'd you do that? Like,
Okay. Can I have side conversations over, please? Let's go back to our basics. Let's say we had 3x squared. What is the derivative of 3x squared? 6x. So you went 2 times 3, right? And got 6? X. And then subtracted 1 from the 2 and got a power of 1. We do the same thing here. We do 2 times pi. 2 pi.
Oh, the R's apply to both. What? I mean, I meant to say this. That's not what I meant to say. The wrong thing came out. Never mind. I answered my own question.
2 times pi times, when you subtract 1 power from the power
I
of 2.
didn't put the square.
Okay, pi r squared was the beginning formula. All right. So now let's talk about we are trying to figure out how quickly is the area changing. So we have an answer of 8 pi, but this answer doesn't really make sense unless we give it a label, a unit. So what are we talking? Are we talking feet? Are we talking inches? Square feet per second. So it's 8 pi feet squared per second.
Isn't it feet per second squared?
I don't think so. I think it's feet squared per second.
I feel like that's really weird.
Did that sound weird? I think it's right. I think it
Square feet per, no, I'm right. It should be feet squared per second. Yeah. 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 Are we okay? One more example?
sure.
Sure. Oh, it wasn't a choice. What I want you to do now is open up to, or turn in your books to page, we're going to go on to the third example. Example 3, an inflating balloon. The first thing you need to do is figure out what formula you're going to use. So I'm looking at example 3. It says air is being pumped into a spherical balloon. See the figure on figure 2.35 at a rate of 4.5 cubic feet per second. Find the rate of change of the radius when the radius is 2 feet. Sounds horrible. We're talking about a balloon, a circular balloon. We're pumping something into it. What formula are we going to use?
4 over 3 pi r squared.
Yes, we're going to go over there. And and by the way, if you look in the very back of your book, look at this, the very back of your book, whole bunch of formulas. There is a sphere formula there, so you will have access to this at home too if you do bring your book home with you. The formula for finding the volume is 4/3 pi r cubed. So that's the first thing that we need to record. Page are we on? Page 151. We're talking about a sphere. And we are talking about pumping something into it, so we are finding the volume. The sphere volume has a formula of 4/3, help me out, 4/3 pi r cubed. Okay, 4/3 pi r cubed. All right, so V, that means this. V equals 4/3 pi r cubed. Let's find the derivative right away. We can figure out what do we need to find and what do we already have. What's the derivative of V?
dv over dt.
dV over dt equals, now, 4/3 pi r cubed. Remember, 4/3 and pi are both numbers, so I'm going to take this 3 and I'm going to multiply it by 4/3. The 3's cancel out. It leaves me with 4 pi r squared. What? 4/3 pi r, or excuse me, 4 pi r squared dr dt. question in the book says when the rate, no, I'm wrong question. Find the rate of change of the radius when the radius is 2 feet. Find the rate of change of the radius. What am I finding? The rate of change of the radius is what? dr/dt. This is the part we're trying to figure out. How quickly is the radius changing? That's the part we don't know. It did tell you what the radius was. What did it say in the book about the radius? What is it? 2 feet. Okay, the radius is 2 feet. So r is 2. And I believe it also told you something about dv/dt2, how quickly the volume is changing. It tells you in here that the volume is changing at a rate of 4.5 cubic feet per minute. So 4.5? 4.5. Our job is to figure out what is dr/dt given that other information. So I need to isolate dr/dt, which means I have to divide by 4 pi r squared. 4 pi r squared cancels out. You okay?
No.
Okay, then go get a drink, whatever you need to do. Divided by 4 pi r squared. This is what we're doing. To find dr/dt, I need to take dv/dt and divide it by 4 pi r squared. So, dr/dt, the radius is changing at dv/dt, which we now know is 4.5, so we take 4.5 and we divide it by 4 pi r squared. So we divide it by 4 pi, what is r? We figured out that that was 2, so 4 pi 2 squared. The hardest part about this is going to be making sure that you type it into your calculator correctly. Make sure you take 4.5 divided by the quantity 4 pi times 2 squared. In other words, you're dividing by 16 pi on the bottom. So we have 4.5 divided by 16 pi. I believe your answer is like 0.09-ish.
How do you plug it into the calculator?
4.5 divided by 4. This Larissa, that whole thing needs to be in its own set of parentheses. Okay, that might be the issue. All right, we were figuring out how quickly the radius was changing. Well, radius is just a straight length. It doesn't have area. It just has a length. So if we are talking about feet, it's not feet squared. It's not feet cubed. It's just going to be that it's changing at 0.09 feet per second. Oh my gosh, how did I do that? 0.09 feet per second. Some of my answers, you're going to notice on my answer key will be left in terms of pi. Sometimes they're not. So just know that on a test, I'm okay with your answers in pi or not pi, whatever you give me is fine, okay? In fact, I was thinking about this. I probably should have left this answer in terms of pi, because 4 divided by 5 is 9/2. I could have easily changed this to a fraction and divided it by that, but